Hi, welcome to me313 Mechanical Engineering Thermodynamics. This is a review of Chapter 4, which is the first law for closed systems. So here are the learning outcomes of this video. First, we're going to go ahead and review the first law energy balance for a closed system. We're going to discuss a couple applications that are relevant to combustion engines, which we'll see more when we move into Chapter 9. I want to quickly review the relationship between U and H for closed systems. This is an application we'll again use a lot in Chapter 9. And then I just want to briefly discuss temperature-dependent energy properties. So first, let's kind of review closed system energy balances. And kind of in a traditional way in thermodynamics, when we look at closed systems, we often use this idea of a piston cylinder. And we use that because we've got a volume where the material inside is fixed, so there's no material going in or out. And then we have this piston, which allows us to sometimes change what the volume of it is. So the energy balance for a closed system, in fact, this is the energy balance for all systems. The change in internal energy, this is the material inside our system, is simply what you put in minus what you take out. Energy can't be destroyed, it can only be moved. Now with closed systems, we have a fairly simple right-hand side of this. Since we're not allowing any material to go in and out of our system, we can simply have two types of interactions: work interactions and heat interactions. Right? And so work interactions, primarily what we'll be often interested in is boundary work, those work interactions which are required to go ahead and change the volume. And then any heat interactions might be go ahead and, again, you might have some sort of electrical heater going into there. But those are pretty much the only interactions we're going to be interested in. Now we move into Chapter 9. We're going to be looking at a lot at engine systems. So essentially car engines. You can think of it as automobile engines. And so one of the things about that is the pistons move within these cylinders really fast. And what that means is they move really fast that usually, going back to this energy balance, only one of those four terms occurs. There's not enough time for the other ones to happen. There'll be multiple steps and we'll have different applications of them. So, for example, here I kind of show a little animation of a internal combustion engine, and see these pistons are going up and down, and we'll actually divide this into kind of four different states. What we'll have is we could have an expansion, which would be when the volume increases. We'd have a compression when the volume decreases. And then we're actually going to also look at the state when it's right at the top, which is top dead center, or right at the bottom, which is bottom dead center, because there's actually heat interactions that are going in on there. So another sort of simplification we can use is that the material inside here is primarily air. There's only a little bit of fuel, and we're actually just going to approximate that as air, which means the left-hand side of this, our energy, we can go ahead and assume that's an ideal gas, and we can go ahead and replace our change in internal energy with the mass times C sub V times delta T. So we're going to go ahead and replace our U with CV dt. Now, for the right-hand side, let's imagine just look at when this piston is up at the top dead center, which is when the spark fires. Really what happens is that's a really, really quick heat addition, but there's not any change in the volume. It just goes ahead and the spark ignites and that explosion happens. So there's one instance where we just have one term, which would be our Qn term. We could look at another instance, like maybe when the piston is going down. That's known as the power stroke. Since it is expanding, that is work coming out of the system. That's all we would have. And it turns out there's not any heat addition to it. Again, it's not happening, or it's happening very fast. There's not time for much else. And so what we would simply have is this work out term. And that would be an energy balance for two of the states. We'll look at more of this in Chapter 9, but hopefully you kind of remember energy balance for a closed system. I want to mention one other thing. We've got an ideal gas, so we're using mCV delta T. One of the things you might be wondering as you look at that is say, well, the volume isn't constant. Why am I using C sub V? And I want to remind you, anytime you're replacing delta U, internal energy, you use CV, even if it's not constant volume. Anytime you want delta U, it's C sub V. And also, anytime you want delta H, it's C sub P. So let me kind of look at one other engine briefly, and this is the diesel engine. And actually, I think I got an animation here if I can get this to show. Hold on a sec. There we go. All right. So this is a diesel engine, and it looks a lot like what we were looking at before. But what's different here actually is that instead of a spark firing, what actually happens is this piston is compressing, and then the fuel is being just slowly added in, and it's being added in as that power stroke is going down. Well, again, we'll look at diesel engines a little bit more, but in that case, our energy balance, again, starting with our energy balance, it looks like this. If we applied it to that one cycle, it turns out we'd have two terms here. The heat addition, because as that fuel goes in, it's getting burned, but at the same time, the power stroke is coming out, and you've got this work out term over here. And this is a minus term because energy is leaving the system as it expands, but you're adding fuel into it. So we've got a Q and a W term in here. However, in this case, one of the things that happens is as that piston is getting pushed down, it's actually a constant pressure that's happening. It happens very fast. Your car doesn't change in acceleration very much during one firing of your engine. So it's actually pretty constant, which means this boundary work term, you could really just call P delta V. The pressure is constant, and you're going to have a change in volume. And the reason I mention it, because you remember, anytime you've got this P delta V term, you can go ahead and put that right in over on the left-hand side, and you end up with what kind of looks like what we saw before, a nice simple one where we've got an energy term equal to a single value, which is like maybe a Qin or a work in. And here I've got a Qin term that I'm going to put in there. And this is the case where I've got delta H. Anytime you want, you're going to go ahead and replace delta H with C sub P. This happened to be a constant pressure, but it doesn't matter. Anytime you want to replace delta H, you use CP delta T. One last thing I want to talk about is just talk about heat capacities. And so we just kind of looked at the substitutions we were doing for ideal gases, right? Delta U is CV dt, delta H is CP dt. But one other thing we're going to notice when we start looking at combustion engines is actually as you go between these cycles, you're actually going to be doing some pretty extreme cold to pretty extreme hot. The air comes in around room temperature, but when an engine fires, it's actually up there at 1,000 degrees or more. And so because you've got very, very large changes in temperature, those heat capacities are not constant. And we can't really get a very good approximation of that. It would be a rough approximation of the energy, but it's not very accurate. It would be nice to have a more accurate change because you're changing hundreds to 1,000 degrees. If you wanted a really accurate answer, you probably remember, oh, I just need to go ahead and integrate that. I'm going to put in some sort of temperature dependence for my C sub V or C sub P values. And that's, it's straightforward, but it's a whole lot of work, and I don't expect you to want to be doing that all semester every time you've got to do this for each set of a combustion cycle. Well, there's actually kind of a nice thing you can do. You can go over to table A17. A17 is ideal gas properties of air. And what this is it gives a listing of what the U values and H values are as a function of temperature. So what you can actually do is just go ahead and say, oh, I'm going to go and say from 210 to 240. You can just read the values right off that table. And that is effectively doing that integration for you. So you remember, internal energy for ideal gas, it's only a function of temperature. And you simply look up your two energy values off a table like that, and you can go ahead and find out what your change in internal energy is. Same thing happens with enthalpy, right? This first column over here is enthalpy. The third column over there is internal energy. You can just look up those values and plug them right in. So, okay, well, that's it for a quick review of Chapter 4. I will see you in the next video for a review of Chapter 5.